Hi class, I'm here to talk to you a little bit about stream discharge and floods. We're going to focus primarily on stream discharge in this lecture. We won't go into floods. We'll make another video for that. Basic idea here is in the lab today, you're going to look at how much water is moving through a stream or a river system. And that depends a little bit on the shape of the channel and where you are in the system. Steeper gradients will have higher velocity, so if you look over to my right, we'll just use this pen tool, up here on the right-hand image in the cartoon, you'll be at a steeper gradient or a steeper slope, right? So the slope of the valley will be like this. You sort of change in elevation over distance. Okay? So the valley up here at the high elevation is going to be steep, and then it's going to curve down. So as you come down to this segment, the gradient will be less, and so the velocity will be less. We measure river discharge as a function of a number of things, but primarily it has to do with where the water level is in the system. So if we come over to the picture on the left, you'll notice it's actually almost very dry in here, but you can imagine that this whole area that I'm drawing in red would be filled with water at some point. Okay? If you had a really big amount of water moving through the system, you might get this whole stream channel filled up. And so we need to know a couple of things about this system. Right now it's basically dry. If I go to my little cross-sectional cartoon on the bottom, we can see again I have a stream channel here. Here's the base of the channel, and then here's the top of the water level. So if I look at that shape, it's kind of a curved shape with a flat top, not quite a semicircle. That's an area. If we were to calculate the width and the height of it, we could determine its area, and that's depth times width. And then the other component of the stream velocity will be the velocity, as I draw this arrow here, in feet per second. Okay, discharge is measured in feet per second or meters per second. Okay, and so we need to know how fast the stream is moving. If we come back to this, sorry about that. If we come back to our image here, we see a person from the USGS, and they're standing in the stream. They have a tape measure here, and they're measuring their distance from the bank. And then in their hand right here, they have a kind of digital flow meter that goes down underwater, and they're measuring down here how fast the water is moving, okay, past them. So they'll stand with themselves downstream, water is flowing in this direction towards them, and this little impeller, like a propeller on a boat or something, is turning and calculating its rotations per second to give us an approximate velocity. So he's creating an average velocity calculation across the stream. It'll be different at different depths, and it'll be different at different positions relative to the bank. So how do we calculate the area of this complicated shape, right? The shape here is not a rectangle. Well, the way to do that is to break it up into many small rectangles, or squares, in this case rectangles. Measure their length and their width. So I can break this guy up into a rectangle here, this segment down here into a rectangle. Now I just use straight line measurements, right? Measuring the length times the width gives me the area. Turns out that if I know the velocity, which is here, okay, the velocity, which we're not going to measure directly in class, but I have a way of doing it on your lab. You're going to take that velocity and you're going to multiply it by the area. Okay, so area times velocity will give us the discharge. Discharge is the amount of water, the volume of water moving past a point. In this example, be past this person and his little flow meter, past a point in a given time. Okay, so here are the basic relationships, right? Area is just length in feet times width in feet. If you wanted to, you could substitute meters in here. Okay, meters would be fine. We're doing it in feet. We want to read/measure the velocity. So velocity is just distance in feet divided by time. In this case, time is in seconds. So now we have two measurements, feet squared and feet per second. If we want to measure the discharge, the units will break down like this. some number of feet squared, right, which is your area, times feet squared, or sorry, feet per second, which is your velocity, gives you cubic feet per second. Okay, cubic feet per second is how we measure, or the units in which we measure the velocity or the discharge, the discharge of a stream, right? Velocity is distance over time. Discharge is cubic feet or volume per second. So here you've got your lab. This is page, this should be the second page of the lab I've given to you. Just a note, there are a few things to do on the first page, so make sure you go back and look at the first page and fill that in. Now, this lab, you can't type on it because it's a PDF, but I also gave you a table for you to fill in and use so you can just type your answers into the table and upload it. If you want to write your answers onto the lab, like print it out and then upload that, that would be fine as well. But let's just walk through our calculations here. So we have a stream channel, and I'm going to outline the base of it in red. Okay, you can see it's in dark. It's a dark color, right? And if I just erase that, it's a pretty bad line since I'm drawing with my mouse. All right, you can see it here. I'll draw it real slowly. There's the base, okay, coming around like this. Now we have a horizontal measurements made for us already. So you see this A, B, C, all the way over to H, which correspond to the stream sections here. They're all 1 foot. So the way this is set up for you is that the stream is flowing in and out of the screen. Okay, and we're measuring across the cross-sectional area in 1 foot increments. Okay, and then we have depth, also measured in feet. And you'll notice here it's 0.25, so that's 1/4 of a foot. Here is 1 foot, and then here is 2 feet. So at its deepest, this stream is about 1.75 feet. Okay, we're going to do each increment, each row as a separate calculation, and then at the end we will sum up those calculations to get the total stream discharge. So let's begin with A. A is a rectangle, you can see it here. Okay? The width is 1, so we've already got all those filled in there, 1, the width of section. Now, the depth has been measured for you. We measured down on our scale to about here, and you see it's close to 0.5, but not quite 0.5, so we've got a depth of 0.4. Now we want to measure the area, so it's length times width. 1 times 0.4 is 0.4 feet squared. Okay. Now the next measurement we need is velocity. I could just give you the velocity, or you'd have to go out into a stream and measure it. Instead, what we have are contoured velocities through the stream. Okay. And you'll notice they're written here in feet per second. This is 1 foot per second, 3 feet per second, 5 feet per second, 7, 8, 9, and 10. So the stream is moving most quickly up here. And then as you get closer, move down 1 layer. As you get closer to the bottom of the stream, the velocity is decreasing. So it goes from 10 feet per second, okay, down to 1 foot per second down along the bottom. And that's because there's friction between the water and the bottom of the stream channel. So what we're going to do to evaluate this is we're going to measure down, and we're going to try and get an average velocity in each of these segments. So an average for A, an average for B, average for C, average for H. Okay? So the key is you measure down 6/10 or 0.6 of the depth. Okay? So 0.6 is about 0.25, right? So in this case, I would measure down and go to the middle of this thing of A, measure down to 0.25, and I would say, what field am I in? Right? Am I in the 1 feet per second, 3, the 5, the 7? I'm in the 1 right there. So then this becomes 1 foot per second. Okay? No problem, right? That's pretty easy. Now all we have to do is multiply through. Okay? So we've got cross-sectional area times stream velocity. Okay? Cross-sectional area times stream velocity. 0.4 times 1 is 0.4. Okay? Let's do B. Here's B. Width is done for us at 1. The depth is, we're down just below 1 foot here, so we're at about 1.1. Okay, 1.1. Okay, cross-sectional area then becomes 1 times 1.1, which is 1.1 feet squared. And I probably won't continue to write that, it's a little awkward. Okay, now what's the velocity in B? Well, the velocity, we're going to come up to B, we're going to measure down 6/10 of 1.1, so it's just over a half, right? So just over a half. We want to know what region this little dot is right here. It's in the 3 feet per second region. Okay, so this is going to be a 3. And so the calculation here becomes 1.1 times 3, which becomes 3.3. Okay, so 3.3. At C, we'll do the same thing. The width has been measured at 1. We'll measure the depth of this, and we go down here all the way to the bottom, come across on our scale, and we're just below, let's say we're like 1.4. Okay, 1.4. Now we know the cross-sectional area here is 1, which is this width, 1 times 1.4, which gives us 1.4. Next step, you got it. We got to figure out, well, what's the velocity? So we have the velocities in here in this set of contour lines. So we're going to drop down 6/10. Okay, which if the depth of this thing is at 1.4, which is here, and this guy is 1.4, okay, this guy was, let's see, 1.1, 1.1, this is 1, this is 3. What's the depth here? You're at, or not the depth. Depth is 1.4. What's the velocity? What's the field you're in? Well, you're in the 5 feet per second, so this would become a 5. Okay. So let me just fill this back in. 0.4, 3.3. Now it's 1.4 times 5. Gives us 7, so this becomes 7. Okay, we can do one more together. I think you're getting the point here. So we'll go up to D. I'll try not to mess up my slideshow by erasing everything I just wrote in here. We get D, 1 foot across. So 1 foot across has already been done for us. We want to measure the depth, the full depth of this down to the end of the rectangle, which gets us, close to the base of the stream. We come across at 1.5. Yeah, you could go 1.5, 1.6, right? 1.6. Now that's 1 times 1.6 gives us 1.6 cubic feet. We need to know where we come down halfway plus a little bit, right? That puts us roughly in, if we come down right under the D, halfway plus a little bit, puts us on the boundary between, let's say, 5 and 7 feet per second for our velocity. So let's say it's 7. 7 goes in there. 7 times 1.6. 11.2. Okay, and then if we were done, if we were just D was the end, we would just sum these guys up. Okay, so the total velocity here would be the total discharge, excuse me, would be 0.4 plus 3.3 plus 7 plus 11.2. okay, which would be 21.9 cubic feet per second, right? That's just for these first 4 columns. So the remaining columns you need to finish up yourself. You want to add up all of them together and put the sum down here. Now, one point that gets confusing is that this is average stream discharge. Do not divide these numbers by 1, 2, 3, 4, 5, 6, 7. Do not add them and then divide by 8. Just add them. We've already taken the average velocity and a known area. So by summing these, you're going to get an average discharge. Okay. There's another problem just like this for you to work on the as a third page of your lab, and that'll be it for your lab this week.